Okay, last thing, I just want to re-emphasize the connection between electric field and force, because we spent a lot of time finding the electric field near objects, and then a common question is, what is the force experienced by something put into that electric field after you've calculated how big the electric field is? And the way you calculate that is if you know the size of the electric field and you're asked what the force is on an object tossed into that electric field, all you do is you take the electric field that's sitting there and you multiply it by the size of the charge that you just tossed in to the electric field. In light of this, we're going to start off class with sort of a sweep-up example involving a disk and the relation of force to electric field. So hop to this one and give me your ABCD cards when you're done. There's also a follow-up here. It asks for sigma, but you can also find the total charge. Think of how you do that. This positive charge is a proton, by the way. Who would like a little more time on this one? Everyone else is pretty much done? A couple more? All right, wrap up what you got. I'll give you another minute, actually. I'll give you another minute. Okay, on the count of three, show me what you got. 1, 2, 3. Who's saying it out loud? There's extras right there. Okay, so I see a mix of B's and C's, which is good. The only difference is the minus sign, which I'll explain towards the end. The electric field is going, or the proton is being pulled towards the disk, is what will determine the sign. All right. The numerics of this problem. So this is a pretty classic problem. It's not like a trivial problem, but it's definitely one you need to know how to do. Okay? It tells us the size of the force on the proton, and we're asked what's the charge density of the disk that causes that big of a force. Okay, so we know the formula for how big the electric field is over in this area. And in order to obtain the force, the instruction is all we do is we multiply the electric field by the charge of the proton. Right? This formula right here gives us the formula for the force a proton will feel when placed in an electric field of size E. Okay, so the electric field, the equation I gave to you down here, it's on a bunch of the slides in other places. So this is just a matter of replacing what used to be the letter E here with this expression. Okay, so here's the equation we generated. This tells you how big the force will be on a proton placed, I don't know, z distance away from a disk of charge, density sigma, and radius a. Okay, this is the expression for the force that proton would feel. Okay, now we look at this. We have one equation, and every number in this equation except sigma is given to us. We are told F, Q of the proton is 1.6 e minus 19. Epsilon 0 is a constant. Z is the distance away from the disk. I wanted to quickly bring to everyone's attention, when I say the distance away from the disk, I mean the disk is like this, and the distance is looking down the barrel of the disk, this distance away. It's not like this. This is not the orientation I ever mean when I say you're 10 centimeters from a disk. It's always you're staring down the circle this way. Okay? I think some of my drawings may have confused that. So Z is, oops, sorry, I wrote 2 centimeters. I meant to write 5. Z is the distance away from the center of the disk that you are, so 5 centimeters. And A is the radius of the disk, which, oh, no, I see what I, sorry, I drew my arrow way too close. Z is the distance you are from the center of the disk, which is 5 centimeters from the diagram. And A is 2 centimeters, the radius of the disk. So if you just plug every number in here, you're going to get that the force, you're going to get force equals, which is 3e minus 19. You're going to get equals a gross number times sigma. I have it written down what the gross number is somewhere else. It's 6.5 e minus 10. And again, that's just from substituting numbers into that giant formula and simplifying everything except sigma. You divide over, and you get 4.64 e minus 10. Now, the question is, what sign is that charge? Because we've always been dealing with the absolute value of the sigma. We haven't considered the direction. So the proton gets sucked towards the disk, and protons get sucked towards minus charges. So the answer is going to be C. Any questions on that? Yes?
Which variable is the charge density? Is the 1, 2?
Yeah, sigma or eta. I use those symbols interchangeably. This symbol represents the charge density. Okay, and then the follow-up, if you were asked what's the total charge on this disk, you have the charge per unit area. Just multiply by the area of the disk, which is pi times 0.02 squared. Yes?
Are we supposed to know the charge of a proton?
He asked, are you supposed to know the charge of a proton? And the answer is absolutely, 1.6 e minus 19 coulombs. OK, so a reminder of Gauss's law, since this lecture is supposed to be about Gauss's law. First step in our Gauss's law process was sketch the field lines near whatever charge you're trying to find the field near. Okay, I'm going to use the example of a point charge just to remind you of how it works. You sketch the field lines just based off of looking at the setup that you have. Next, Next, you draw a surface, which you only really have 3 options, sphere, cylinder, or box, through which all the arrows are perpendicular and equal size. So in this case, I'm doing a spherical shell. And again, I put this on the previous slide, so if you don't have enough time, don't worry, you can always go back and look through the slides later. In this case, since the electric field is the same size everywhere on the area, and it's always perpendicular, the electric flux side of Gauss's law is just E times the total area. And if you remember, Gauss's law is phi equals Q enclosed over epsilon 0. So E times A equals Q over epsilon naught was our formula for Gauss's law. But it only worked because we're working with a very specific surface that we drew. Then our general procedure is pretty easy. You write down the expression for the area of your Gaussian surface, and then you find how much charge is enclosed by it, and then you divide the area expression to the other side to get the answer. Again, this is just a review of what we did last class. Okay. Something we missed from the end of class last time was the electric field near an infinite plane. Now, if you remember, when we did this the harder way, we had to do a disk and take a limiting case of the size of the disk being very large. And that was pretty hard because the disk is really hard. But as usual, Gauss's law makes it pretty easy. So let's say I have a nice, large, infinitely extended plane of charge density sigma. Okay, again, that's charge per unit area on the plane. Step 1 is we're going to draw, just by sketching, what the electric field arrows look like. And in the case of a plane, we know that it looks like this. Okay. Now, our next step is to draw a Gaussian surface through which all these arrows are perfectly perpendicular, except maybe the edges. If you remember how we did the infinite line, we allowed the edges to have parallel parts. So we need to draw a surface through which all these lines are parallel. And we have three options: a sphere, a cylinder, and a box. What do you think is a good idea? A box, yeah. So we're going to draw a box, and sort of like how for, actually I'm going to use a different color for our imaginary surface. Sort of like how for the cylinder, we sort of introduced this length of the cylinder L in our derivation, and it canceled out later. We're going to assume that this box has a cross-sectional area that I'm going to call B, just some variable. So the size of this surface right here is B. I'll write it in red. Okay. And we're going to call the still unknown size of the electric field at that box's surface, we're going to call it E. Again, as of right now, that's an unknown number, but we're going to use tricks to find what it is. And also, as usual, I'm going to position the box a distance r away from the surface of interest that I'm leaving as a variable for now. Okay, now we just go to town. So the electric field, or sorry, I should say the electric flux enclosed is equal to the charge enclosed divided by epsilon 0. And as usual, we're going to work the left side and the right side through one step each. So the charge enclosed by this box is pretty simple because we know the area of the box, B, and we know how much charge per unit area is on the surface. So it encloses this green little rectangle of charge, right? That has area B and charge density sigma, so the Q enclosed is sigma times B. Okay, now we're going to work the left side. The electric flux through this box's surface. Now, just like in the cylinder case, the edges contribute 0 flux because the electric field is parallel to those surfaces. Again, that's sort of like how in the infinite line, in the E times A part, we didn't count these areas at the end of the cylinder because there was no electric flux going through them. So it didn't enter into the total flux. So we only use the area of the actual cylinder part of the cylinder. Similarly here, we're just going to use the total area of the box that has the arrows going through it, which is this top half and the bottom half. So the total area is actually 2B that you use on this side. Okay, and the reason they don't cancel out to 0 is because the flux is going outwards from the box in both cases. There's 2 outwards fluxes. Okay, now all we have to do is divide 2B over to the other side and the problem's done. So Q is actually just sigma times B. The B's cancel, and we got our answer of E near a plane is sigma over 2 epsilon 0. How wonderful is that? About one step. This extra factor of 2 here, it can be confusing for some people. If you are confused, I can't go over it again because I need to get to some other stuff today on cavity conductors. But feel free to rewatch the lecture and come up to me and ask if you have more questions on that. Yes?
So, can you explain how you got Q equals the
Sigma times B? Yeah, so he asked, how did I get Q enclosed by the box is sigma times B? So the box encloses this little rectangle of the charged plane. That box has area B, or that square has area B. And I know sigma, which is how much charge per unit area there is. So I just multiply the charge per area times the area.
Oh, so sigma is the charge per area?
Yes, sigma, as always, sigma is the charge per unit area of the plane. Similar to how in the charged disk problem you were worried about what is sigma, how much charge per unit area is the disk, how charged up is it? That's what sigma is here. Yes. Okay, one more Gauss's law example, and this is a good one, and you're going to do a similar one on a homework. This is for a fat wire. So last time we did a wire that was just like a point. This time we're going to do the wire itself is a little bit fattened. It has a radius. It's like a real wire. This is how real wires look. Okay. It has radius A and charge density. This is charge per unit volume this time. It's just like sigma, but one dimension up. Rho. Okay. Let's handle the case inside the cylinder, which is the more difficult case. So just by the symmetry of the problem, I know that the electric field points radially outwards, just like it does for the simpler case of the wire. It's kind of really hard to draw, so my apologies. I'm going to actually erase some of these. Okay, let's draw our Gaussian surface. And at this point, you don't even need me to tell you that you should pick a cylinder, because the sphere and the box are kind of stupid for this example. So we're going to pick a cylinder at general radius little r from the center. Okay. And just like in the last time, we're going to give that cylinder a length L that will drop out in our final answer. Again, it's a distance r away from the center. Sorry if that is a little small. I think I should have made my diagram a little bigger. Okay. We've drawn our cylinder. Now we're going to write Gauss's law out, which is E times A is the enclosed charge by that imaginary surface that you've drawn over epsilon 0. Okay, surface area of a cylinder here. Again, we aren't going to use the area of the caps of it because there's zero flux coming from those because the arrows are parallel to the surface. So we're just going to use 2 pi little r times L. That's the circumference times the length. And again, I'm using little r for the area because it's the area of our surface at general radius. I'm not plugging in A. This works for the cylinder at all distances r. Okay, the only thing that's left, and then the problem will be solved, is to find Q enclosed by that cylinder as a function of little r. Now, we know the charge per unit volume of this fat wire, and we also know the volume of the cylinder. What's the volume of a cylinder? Yeah, pi r squared, the area of one of the caps, times the length. So all we need to do is multiply the volume of that imaginary cylinder we drew times how much charge per unit volume there is, which is rho, right? This is saying that Q equals rho times volume. That was from a couple classes ago. And I plugged in the volume of the cylinder. Okay, now I'm just going to move this over to the other side, and the problem's done. Actually, I'm not going to box this for a reason I'll explain in a second. Okay, everyone good copying that down? Again, it's the exact same process as last time, just a little bit more complicated to find Q enclosed by the surface. Okay, I'm just going to make a comment. So I didn't box this, and it's because people accidentally apply this to cases that they shouldn't. This only works for a fat wire with constant charge density rho that doesn't change depending on how far out you are. And it only works inside the wire. As soon as you go to R greater than A, this does not work anymore because this formula assumed you were enclosing only like charged stuff. Once your imaginary cylinder gets outside, that formula for total charge no longer works, and you would use the volume of the whole wire. Okay, so this is just an example of a way you can use Gauss's law for a more complicated problem. And one final remark is this electric field actually gets bigger with radius. Okay, we're used to seeing R appear in denominators, either as 1 over R for a line or 1 over R squared for point charges. This actually gets bigger with R, and this is typical for what you'll see inside of charged objects, such as within a charged sphere. You'll see that the electric field grows as R squared. Yes? The question was the charge is inside the wire, and the answer is yes. The wire is sort of each unit of volume is loaded with a little bit of charge. For Q enclosed? Yes. So his question was, why are we using volume in Q enclosed when in the last part we were in the infinite plane we were using area? And the answer is this is a 3D object which has charge per unit volume. And in the last problem, you had a 2D object which had charge per unit area. Okay? So a natural extension of this is, what if rho was not the same everywhere in the wire? So in that example, it was uniformly charged per unit volume. But a question is, what if rho were some constant times, I don't know, R squared? So the charge actually was 0 at the center of the wire per unit volume, and then as you got out further, the charge per unit volume actually got stronger. This can happen in real wires, by the way, especially in the presence of magnetic fields. But for now, it's just an example. What if I built a wire with a different spread of the charge? And the answer is, the only thing that changes is that determining Q enclosed, you can no longer just multiply rho times volume, right? Because rho is not the same everywhere in the volume. Okay, instead, we have to integrate rho dV to get the total charge. And you integrate it over a volume of your Gaussian surface. So just a sketch, I'm not actually going to do this problem out. We're going to use, for dV, and again, I'm not actually going to do this problem out because it's a little bit tougher. We're going to use one of these formulas for dV for a cylindrical shell. So the bit of volume associated to a little bit of cylindrical shell of radius change dr is 2 pi r L dr. Okay, that gives you the area of this little region, the volume of this little region in between the outer shell and the inner shell. Okay, you imagine if there's like a straw and then a slightly thicker straw, this tells you how much volume is enclosed in between those two. And the way you get that formula, if you ever need it, is you start with the volume of a cylinder. and you take a derivative with respect to r, which brings down this 2. And since you're doing d of it rather than d dr, you leave the dr at the end. Okay, so in this case, you would be integrating rho 0 r squared. That is what rho was in our problem. It changes depending on r. And then you plug in dv, which is 2 pi r L dr. So you would be integrating r cubed dr to solve the problem. Again, this is just a light sketch of how you would approach one of these problems, but we're not going to do one of these problems. Question, yes?
Are you saying rho to the power of r to the power of 2, or just rho times r to the power of 2?
It's just rho naught is some constant. It's like 3r squared might be the function. Okay, again, this is just a sketch. The only thing that changes when rho is in constant is you can't multiply rho times v anymore. You have to integrate rho dv. Here's just a reference table of all the dv's for common objects. Don't copy this down. No, don't copy it down. OK, next topic. So Gauss's law is, well, not totally done, but we need to learn a little bit about electric fields near conductors now. This is a pretty common topic. OK, so when you have a conductor, let's say this little blob right here, let's say this shaded area is a conductor. There's a general principle that you'll just kind of want to memorize for now, but you can understand why later. It's that the electric field inside a conductor is 0. I'm going to be more specific. The electric field inside the actual material, maybe not in this gap in the middle, but inside this shaded material, it is definitely 0. Okay. And the reason that this is so is, imagine if the electric field inside the conductor were non-zero. Okay. Now, if there are any charges in the conductor, which a conductor is made out of atoms, so there's charges inside it somewhere. If the charges would be subject to an electric field, a conductor, there's no resistance to motion. There's nothing holding them in place, unlike insulators. So if there were an electric field, the charges would start flying around, and the substance wouldn't be at equilibrium anymore. So you'd need to wait for it to settle for a couple seconds. But when it settled, it had better have electric field 0. Okay, so E field within the body of a conductor is 0, because if it weren't, charges would be about to start launching themselves around. So as long as you wait the couple seconds for the object to settle, which is always assumed to have been done, electric field is going to be 0 inside of a conductor. Okay, now we can actually use this to our advantage. let's imagine we're zooming in really close on the edge of a conductor. So inside of this is a conductor, and the conductor just goes on forever. And we're going to look for the electric field just outside of the conductor. So to a good approximation, it's a plane. Okay, now we're going to use Gauss's law for this. It's a plane. I'm going to draw a rectangle. Okay, now I'm going to go through this derivation just a hair faster, so I'll leave out some of the intermediate steps. So as usual, we have the total flux, which is E times A. But we only count the surfaces that have the electric field punching through it perpendicularly. In the previous case, there was an electric field here as well. So we had E times A flux from the top surface and E times A flux from the lower surface. So in the previous problem, we used E times A times 2 because there were two surfaces with EA. But now there's no flux through this bottom surface. So there's only one factor of EA coming from this top region right here. So I think I used B in the last example. So B is the area of the box. Okay, and just like last time, the conductor is allowed to have charges on its surface of density sigma. So the amount of charge enclosed by the box is the same as last time. It's the area on the surface, which is B, times however many charges per unit area there are. Okay, the only difference is there's no 2 on the left side of this equation because there's no electric field on this lower edge. Okay, so I divide both sides by B. And I get something that looks really similar to the last equation for the infinite plane. The only difference is there's no 2 in the bottom. And that's because this is a conducting surface. And in the previous example, it was an insulating surface where the charges were glued to it. Here, the charges are just coincidentally sitting still. But there's a difference of a factor of 2 in this formula compared to the last one. Okay, we'll start off next class with an example problem on this. By the way, you should be able to do almost all of homework 2 by now. There's only 2 problems that you might not be able to do, maybe 3.